welcome back. So in this video we will be discussing one function of two random variable, that is by taking an example of z equal to x plus y, where x and y are two random variables and the joint PDF of x and y is given by fx y x comma y, right? So the function of x and y, right, is a variable, a random variable z, right? And for this case we will need to evaluate fz of z, right? So we can start this with a very simple step, that is by taking the cumulative distribution function of fz of z, fz of z. So we know that fz of z is nothing but its probability of z less than or equal to z, right, which is equal to probability of, so I'm just going to simply replace this term here. It is g of x comma y less than z, and we very well know that this is going to be integral over the region dz f x y x comma y dx dy, right? So this is all what we are going to do. So let us now take our example, that is let z equal to x plus y be our example, and I'm going to replace this term here, that is fz of z equal to probability of z less than or equal to z, which is equal to probability of x plus y less than or equal to z, right, which is again the same thing, that is integration over the region dz f of x comma f x y x comma y dx dy, right? So let us try to plot this region, right? Suppose we have equation z is equal to x plus y. We will need to plot this equation. It's as simple as I just put values of 0. So if you make x as 0, my y is going to be equal to z, and if I make y as 0, my x is going to be equal to z, right? So if I have to plot this equation here, it is going to be 0 comma it is going to be 0 comma z, right? It's going to be 0 comma z, and here it's going to be z comma 0. So I can plot this here, and this is x and this is my y, and we have an inequality here, that is x plus y less than z. So it's going to be this whole region x plus y less than z, right? So if I have to integrate it over a strip, right, let me consider it over a strip. We know that the y is ranging from minus infinity to plus infinity, right? But if you observe this x, it's from minus infinity up to this point, right? So what is this point? What do we know? That is z is equal to x plus y. So x, which implies x is nothing but x equal to z minus y, right? So if I have to integrate this, right, let me just write fz of z again. It's going to be y is equal to minus infinity to plus infinity integration x equal to minus infinity to z minus y f x y x comma y dx and dy, right? So what do we actually need? We are going to find fz of z, right? We are going to find the probability density function. So what do we have here? We have CDF here. So how can I find this fz of z? It's nothing but it's d by dz, right, of fz of z, d by dz of fz of z, and it's going to be fz of z is equal to d by dz of integration y is equal to minus infinity to plus infinity integration x equal to minus infinity to z minus y fx y x comma y dx and dy. So this particular equation we are going to evaluate by using Leibniz rule. So Leibniz rule is not something which is very complex, it's very simple, right? So let h of x equal to integration the lower limit a of x, upper limit b of x, h of x comma y dy, if this is given, right? Using Leibniz rule we say that d by dx of h of x, right, is equal to d by dx of the upper limit, this is our upper limit, into h of that's a function, h of x comma, so replace this variable of integration by the upper limit, so replace the variable of integration by upper limit minus d by dx of lower limit, that is a of x, into h of replace the variable of integration by the lower limit. It's not done, plus we have one more term here, that is a is equal to that is lower limit a of x b of x d by dz of h of x comma y dy. Okay, so this is going to be our Leibniz rule. And what do we have to do here, right? So where did we start from? That is h of x, right, minus infinity to infinity h of x comma y dy. Fine. And let me write our equation, that is integration y is equal to minus infinity to infinity integration x equal to minus infinity to z minus y fxy of x comma y dx into dy, right? So what were we evaluating basically here? The same equation, right? So this is going to be our, this equation is nothing but this one, right? Capital fz of z. So let us start applying Leibniz rule to this, right? So we need to apply Leibniz rule two times. First is to, before we penetrate to the inner function, so we will have to apply Leibniz rule to the outer integral, and then we'll go to the inner integral. So applying Leibniz rule first time. So first time we are going to apply Leibniz rule, that is going to be d by dz of fz of z, right? So right, this is what we are trying to find out. So d by dz of fz of z, because we need the PDF of z, right? So d by dz of fz of z, this is equal to d by dz of the upper limit. So what's our upper limit here? It's infinity. So replace the variable of integration here x y by the upper limit, that is x comma infinity, minus d by dz of that is the lower limit, and replace the variable of integration by the lower limit. So this is going to be minus infinity fx y x comma minus infinity, right? The next term is going to be plus integration. The next term is going to be from that is from minus infinity to plus infinity, minus infinity to plus infinity f of, let me just again refer this, minus infinity to plus infinity. So we need to write d by dz f of x comma x of y, x comma y, right? And we have a dy here, dy, we have a dy here. Okay, so this term is 0, this term is 0, we are left only with this, right? So let me just write it down here for you. That is going to be 0 minus 0 plus integration. Remember, we started with y is equal to minus infinity to plus infinity d by dz. So what is f of x comma y dy? We had then inner integral, that is x equal to minus infinity to z minus y, right? So here I have written this. Right? F of x y, x comma y, d by dz of x comma y dx, right? Dx, and this dy. Fine. So now we need to apply Leibniz rule for the second time. Okay, so let's write it down. It's very simple. Y is equal to minus infinity to plus infinity d by dz of the upper limit z minus y, and replace the variable of integration. Here the variable of integration is x, so this x needs to be replaced by the upper limit, that is f of x comma y z minus y comma y minus d by dz of minus infinity, that's the lower limit, f of x comma y minus infinity comma y. Nothing here, I have just replaced the variable of integration, that is x, by the I have just replaced the variable of integration here, right? Or have I made a mistake? Replace the variable of integration by upper limit, so this is going to be z minus y, right? Z minus y, and the last term as usual, that is integration x equal to minus infinity to z minus y d by dz of x of x comma y dx dy, right? Fx y, right? So you can see that this term, that is independent of z. So what is going to happen here? What is going to happen to this term? And remember, this dy is going to be outside, right? What's going to happen to this term? This is nothing but 0. So what we are left here with, the differentiation of z is 1 and y is 0. So we will be left here with just y is equal to minus infinity to infinity fx y z minus y comma y dy. This is what we are going to be left with. So we started from here, right? We started from here and we are left with this particular term, and this is nothing but it's fz of z, what we have just found here, and this is pdf of z. So quickly, last few steps. So suppose x and y are independent. So if x and y are independent, what happens is the joint PDF of joint PDF of x and y is given by fx of x comma fy of y. So if x and y are independent, so we can write this as z is equal to x plus y if x and y are independent, are independent, we can write this as fz of z equal to integration y is equal to minus infinity to plus infinity fx of z minus y to fy of y dy, and this equation is very familiar to most of the electronic students, right? So what is this equation? Is nothing but fz of z equal to fx of x. If you have guessed it, you are right. It's convolution, right? It's convolution fi of y. So that's it for this video. Thank you for watching.